All right, hello everyone. So we have now finished chapter 5 and we're going to move on to chapter 7. So section 7.1 is going to be about sets. So chapter 7 is a lot more about statistics than it is really about the math that we have been learning about. So we're going to be making definitely a shift here of subjects. So like I said, section 7.1 is going to be about sets, so we're going to learn some of the basics of statistics in this section. So a set is a well-defined collection of objects in which it is possible to determine if a given object is included in a collection. So an example, a set can include all the students in our class, or all the US presidents, or even all the different pairs of shoes you have. So a set can be thought of any real category that you can think of. So in math, sets will often contain numbers, which is pretty explanatory since we're in a math class. So our sets will contain numbers. So sets are written as comma separated lists inside curly brackets. So whenever you see a set, you'll see it often written as, in this case, we have a set of 1 through 6. So we have 1, 2, 3, 4, 5, 6, and they're inside curly brackets. And so when we write this, when we look at this, we can think, well, okay, this is a set. It's written as a comma separated list inside curly brackets. So in this case, 1, 2, 3, 4, 5, and 6, these are called elements or members of the set. I'll normally call them elements. You can call them either whichever you'd like, so you can call them elements or sets, but I'll normally call them elements. So 1 is an element, 2 is an element, 3 is an element, 4 is an element, 5 is an element, and 6 is an element. So an element is basically just one number or one factor in your set. So to show something is an element of the set, we will write 3, and then we have this symbol. And it kind of looks like the sound symbol for, I believe, a euro or a pound. But it's basically a C with a line in the middle. And we show that to mean that 3 is in. So that symbol signifies the words is in. So 3 is in, or is contained in, or something along those lines. So 3 is in the set of 1 through 6, which makes sense because we know this set has 1, 2, 3, 4, 5, and 6. So we say that 3 is in the set. To show that something is not an element of the set, it's the same symbol with a dash through it. So our symbol is that looks like a C with a line in between, or you can even think of it as an E if you'd like a really funny looking E, capital E in that case. So in this case, we would say that 9 is not in the set of 1 through 6, and that's because 9 is not within the curly brackets or in our set. So we have 9, and then we have our symbol of in with a dash through it. So 9 is not in the set of 1 through 6. So sets can also be represented by a capital letter. So we can set capital A equal to the set of 1, 2, 3, 4, 5, and 6, or the set of 1 through 6. So now whenever we reference A, we know that A is the set of 1 through 6. So we can say 4 is in A, 5 is in A, but 10 is not in A, etc. So you can say numbers in or not A, and we know that A will represent this set. It is also possible to have a set with no elements, and this is called the empty set or the null set. I'll normally call it the empty set, but either name you call it, it's the same thing. So we have the empty set or the null set, and it's written as a 0 or an O with a dash through it, so that a line through it. So an example of an empty set would be the set of people who are more than 10 feet tall. There's no one in the world that's more than 10 feet tall, so this would be an empty set. There's just nothing in it. And a word of caution, the set of 0, or if you write 0 in curly brackets, you'll also see that the empty set will be that 0 with the dash through it, or the O with the dash through. You can also see can be contained within curly brackets or not. But we see that 0 within curly brackets, so the set of 0 and the set or the empty set are two different sets. So 0 is considered a number, and therefore is an element. So if you see 0 in curly brackets, you know that 0 is an element of the set. But the empty set represents a set with absolutely no elements. So the set of 0 and the empty set are two different things. So if you want to say the empty set, you can't write 0 within curly brackets. It has to be the symbol for the empty set. All right, so moving on, we can use the symbol also n with parentheses of, in this case, let's just say a, using the same value of a which we had earlier, to indicate the number of unique elements in the finite set A. So using our previous example, n of a, and that's how we'll say it. That's how we'll say this symbol. So n of a is equal to 6. So we're counting the number of unique elements, and since we're doing 1 through 6, none of our numbers are repeated, so we know there are 6 unique elements. Now, two sets are equal if they contain the exact same elements. So an example, the set of 5, 6, and 7 is equal to the set of 7, 6, and 5 is equal also to the set of 6, 5, and 7, and so forth. The sets 5, 6, and 7, and 6, 7, and 8 are not equal because they contain different elements. They don't have the exact same amount of elements. We also see, sorry, backtracking a little bit, we also see that the ordering of sets doesn't matter as long as the same identical elements are in the set. Ordering doesn't matter. You can write them in any order that you want as long as it's the exact same elements. So the sets of 5, 6, and 7, and 6, 7, and 8 are not equal, so we would write the set of 5, 6, and 7 is not equal, so we write the equal sign with a slash through it, not equal to the set of 6, 7, and 8. And this is because 5 is not in the second set, and 8 is not in the first set. They don't have the exact same elements, so therefore they are not equal. Even though they share elements, this doesn't make them equal. So we also see that each element is only listed once. This isn't always going to be the case, but in the cases that we're going to look at, especially just for this section, we'll only see really each element listed one time. So sometimes we are interested in a common property of elements in the set instead of the actual list. So a common property can be expressed by setting or using set builder notations. This is a different way of writing a set. So instead of having curly brackets with a long list of numbers, instead we can just have a set builder notation to call all the elements that have a certain property. So our set builder notation is within curly brackets we have x, and then it's not exactly very straight, but you would have just normally a straight up and down line. Mine's a little curved there, but it should just be a straight line. So it's just a straight vertical line. We have x, and then x has a property p. So we're stating first that x is our set, or x is our elements of our set. Then we have our line, and then we have that property of x. So we're saying that x is this, or x is something. But the actual elements of the set are just x. So this represents the set of all elements x has the same property p. So if we said x is an even number, then our x would be 2, 4, 6, 8, and so on and so on. And that would be called an infinite set because those numbers go on forever. We're only going to be working with finite sets, so numbers that we can actually count. All right, so for example 1 here, we're going to work a little bit with this set builder notation. So for example 1, we want to write the elements belonging to each set. So for part A, we have x, where x is a natural number less than 4. Natural numbers pretty much are just whole numbers, but they exclude 0. So a natural number less than 4, so whole numbers less than 4 that's not 0, we have 3, 2, and 1. Natural numbers are positive whole numbers, not including 0. I forgot to add the positive part. So positive numbers less than 4, not 0. So if we want to just write the elements that are going to be in this set, we see that the natural numbers less than 4 are 3, 2, and 1. This means our set is 1, 2, 3, or x is equal to the set of 1, 2, 3. Or I guess you just write them in a list. So you'd say x is 1, 2, and 3. All right. So those would be our natural numbers less than 4. So if we rewrote the set to not be in set builder notation, or just our regular set notation, it would just be 1, 2, and 3, or the set of 1, 2, and 3. And for B, we have that X, where X is a state that borders Nevada. So you can also have descriptive elements, not always numbers. So in this case, if we're thinking of X, and X is a state that borders Nevada, we want to think of all the states that border Nevada. So if we want to think about all the states that border Nevada, so we need X, all the states. Nevada. So we know that this set, where X is equal to California, Oregon, Idaho, Utah, and Arizona. So if we wrote the set in regular set notation, this would be California, Oregon, Idaho, Utah, and Arizona. And you see it's a comma separated list written inside curly brackets. So that would be our set where X is a state that borders Nevada. So it's all the states that border Nevada. So in this case, if we wanted to say how many unique elements are in the set, it would be 6, 5. I can count 5. So there are 5 states that border Nevada. So there are 5 unique elements of our set. So we can see that none of these are repeated or anything like that. All right, so that was some practice using our set builder notation. Now we're going to move on. So we see the universal set for a particular discussion is a set that includes all the objects being discussed. So an example in elementary school, the set of whole numbers may be a universal set, because when you're in elementary school, you're really only learning about whole numbers. So that in your mind, whole numbers would be your universal set, since you don't really know about irrational numbers or integers, decimals, or anything along those lines. So the universal set is specified whenever it's necessary, or it's very clearly understood from the problem's context. In no case will we be like, I have no idea what the universal set is and it's asking for it. It's either going to be very clear or specified. Okay, so moving on, we're going to think about subsets. So, I mean, even just thinking about the word subsets, you know, we can kind of think of, okay, well, what's a sub of something? So a subset, maybe a set inside of a set. And that's exactly what it is. So sometimes every element of one set will also belong to another set. So an example, our set of A, which we've been working with, is 1, 2, 3, 4, 5, and 6. And maybe let's let B equal 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So our set of B is all of our values between 0 and 10. Now we see that every element is in A is also contained in B, since 1 through 6 is contained in 0 through 10. So we would say that A is considered to be a subset of B. So it is a set within a set. To express that B is not, so first we're going to work with if A is a subset of B. I think I forgot to write that in. This is written as A, and we kind of have this sideways U. I wrote that very badly, like a sideways U with a line underneath. And that's to signify that A is a subset of B. So it's that sideways U with a line underneath. And it's always that direction. You will never have the symbol reversed. It's always looks like that. And it's always written and known as A is the subset of B. So whatever your subset is, it should be listed first. And then whatever larger set that subset is within is always going to be second or on the right, and your subset will be on the left. And we say if something is not a subset, then it's the same symbol just with the slash through it. But now we reverse this since we know that B is not a subset of A, since there are values in B that are not in A. So we would say that B is not a subset of A. So we have the same symbol with the slash through it. So the book definition of this, we say set A is a subset of B, written as A with our symbol, the sideways U with a line underneath. So A is a subset of B if every element of A is also an element of B. Then also we have this other definition where we say set A is a proper subset, written as A with our symbol is a subset, or that sideways U, of B if A is a subset of B and A does not equal B. So any set is a subset of itself since they contain the exact same elements. So we would always say that A is a subset of A and B is a subset of B. Since they contain the exact same elements, they still qualify as subsets even though they are equal. But a proper subset is meaning that our set of A is not equal to B. So this just means that it's a proper subset. They don't have the exact same elements, but A contains elements that are also in B. So that's the difference between a subset and a proper subset. We won't see proper subsets come up that often unless we're specifically asking if something is a proper subset. Most of the time, we just want to know if it is a subset. So we're going to mostly be using our symbol with our U with our line underneath, our sideways U. All right, working a little bit with subsets here. For example 2, we want to decide whether the statements are true or false. So we have two sets in each one of these, and then we have a statement underneath that we want to check if it's right. So for A here, we have our subset, our set capital A, is equal to 2, 3, and 4. Now we have our set B, which is equal to 1, 2, 3, 4, 5, and 6. We want to know, is A subset of B? Well, the only thing we need to do to check if A is a subset of B is see if the same elements in A are also in B. So our elements of A are going to be 2, 3, and 4. We look at B. Our elements of B are 1, 2, 3, 4, 5, and 6. And well, we definitely see here that 2, 3, and 4 are contained within B. So we say yes. So that statement is true. Well, sorry, true or false. So I guess we should probably write true instead of yes. So true. Now moving on to part B, we have our set A, capital A, is equal to 2, 3, and 4 once again. But B is our set of 4, 3, and 5. Now we're asking, are A and B equal? Well, our set of A has 2, 3, and 4. Our set of B has 4, 3, and 5. So the only elements they really share are 3 and 4, but A contains 2 and B contains 5. So they can't be equal since they don't have the exact same elements. So we would say that this is false, because we're asking if they're equal now, not if something is a subset. Now for part C, we have our set A, capital A, is our set of 3, 7, and 6. We also have that B is a set of 7, 6, 8, and 2. Now we want to know, is B a subset of A? Well, would B be considered a subset of A? The only way that B would be considered a subset of A is if it had the exact same values that were in A. So we see A is 3, 7, and 6. B is 7, 6, 8, and 2. So B doesn't contain 3, so it couldn't be a subset, even though it does contain 7 and 6. But we also see that B also contains 8 and 2, so there's no way that it would be a subset of A because it doesn't contain 3, and then in addition, it contains 8 and 2. So there's no way that would be a subset. So we could also say that this is false. Even if it were the other way around, if we were saying, well, is A a subset of B then? If we were considering that, well, A wouldn't be a subset of B since B doesn't contain 3. So we see that either way, right? That's still going to be false. All right, so now moving on, we see that the empty subset of our empty set, or in this case, our empty subset, so it can be an empty set or an empty subset, is our symbol there, our O or 0 with a dash through it, or a slash through it, sorry, is a subset of every set. And it's considered a subset of every set since it's impossible to find an element in our empty set that is not an element of any set. So subset A is a subset of itself since it contains the same elements. So these are just a few subset properties. So we have for any set A, the empty set is a subset of A, and A is also a subset of A. So the fact that an empty subset can be, or an empty set can be a subset of any other set is more so that we just can't prove that it's not a set within A. Since A contains a myriad of elements, if you took out all those elements, then it would be the empty set. So technically, an empty subset is, or an empty set is a subset of any other set. A little confusing, but you can just memorize the property that an empty set is a subset of any set. And it's more so just that you can't prove it's not. That's kind of where that property comes from. All right, example 3. We just want to list all the possible subsets of each set. So if we want to think about all possible subsets, well, we already know our subset properties. So our empty set is a subset, and our set is the subset of itself. So we can write right off the bat, we know that the empty set, the set itself, are both sets. But now we kind of have to break it down by element. So 3 is contained in our set, so the set of 3 would be considered a subset of our set of 3 and 5. And same goes for 5. So we have our empty set, our set of 3, 5, so our original set, our set of 3, and our set of 5. So we see in this case, we have 4 subsets. Now, for every set, if you want to list the possible subsets, you will always list the empty set, and you will always list the set itself. And then all you need to do is find all the sets in between, or all the subsets in between. So now, for part B, now we have our set builder notation. So part B is X, where X is an even natural number less than 8. So if we're thinking about an even natural number less than 8, we have positive whole numbers, don't contain 0, and they're less than 8. So we can rewrite this as a numbered set, or standard set notation. So we know even numbers less than 8, positive whole numbers not containing 0. This is going to be 2, 4, and 6. So now we have a set where there are 3 elements. We know always the empty set is a subset. The set itself is a subset. Now we need to find all the variables in between. So let's just start by doing the single elements. So 2 would be a subset, 4 would be a subset, and 6 would be a subset since they're all contained in the set. So we say 2, 4, and 6. Now since there's 3, we know that combinations of 2 will also be in the set. So let's just start thinking of some combinations. So we have 2 and 4. That would be in the set. Maybe 4 and 6. That would also be in the set. And 2 and 6 would also be a subset. So here we have the empty set. We have the set itself. We have the subset of 2, subset of 4, subset of 6, and the subset of 2, 4, 4, 6, and 2, 6. And this is going to be 8. So 8 subsets. Now, a good way to find the subsets of 3, 5, and 2, 4, and 6 is to use a tree diagram. So you probably at some point heard what a tree diagram is, but it's just a systematic way of listing all the subsets of a given set. So how are we going to write this tree diagram? We have our set of 3 and 5. And we'll just start with our first element. So we're going to zoom in a lot here. So for this point, and let's use a different color other than black. So let's use red. So let's say, is 3 a subset? And that's our question, sorry, set. And that's our first question, or our first point. And what we want to do is we want to track the yeses and nos. So, well, let's just say yes and no, because there are going to be cases where 3 is a subset and cases where 3 is not. So if we start with yes and no, that gives us 2 options. Then we want to move on to maybe these points here, this row. So 3 is a subset, that corresponds to this row. Now we're going to ask, is 5 a subset? So is 5 a subset? Well, sometimes it will, sometimes it won't. And we have to take this as according to that yes, 3 is a subset. But we also have to do this for thinking about no, 3 is not a subset. And if it's not, we're asking if 5 is a subset, we also have to have our options of yes and our options of no. So then we just want to follow our tree. So if we started at our first point, and we think, is 3 a subset? My cat very much wants to be in the video. If you think, is 3 a subset? And let's take our first branch here. When we say yes, 3 is a subset. Let's just follow our top branch. So if we follow our top branch, we're saying, is 3 a subset? Yes. Is 5 a subset? Yes. Let's follow that arrow. So if we say if 3 and 5 is a subset, or in this case, we're thinking in the subset, I should have written that differently, is 3 in the subset, 5 in the subset. So thinking about this a little bit differently, is 3 in the subset and is 5 in the subset? If they're both in the subset, then our subset is 3, 5. Now let's switch branches. So we're still thinking yes, 3 is in the subset, but no, 5 is not in the subset. So that's going to give us just the subset of 3. So now, switching our first branch, we have is 3 in the subset. Let's go with no, 3 is not in the subset. But is 5 in the subset? Yeah. This is going to give us the subset of 5. Then we think, is 3 in the subset? No, 3 is not going to be in the subset. But is 5 in the subset? We're also going to go with no. So if 3 and 5 are both not in the subset, that's going to be our empty set, since there's no elements essentially in our subset. So we see we can use these tree diagrams to kind of separate out thinking about, is this element in the subset, is it not in the subset, and this way we found each one of our subsets. Now moving on to 2, 4, and 6, we see our tree is going to get larger because we've added another element. Starting with our first point here, we want to know, is 2 in the subset? Starting here. And then of course we're going to have yes, we're also going to have no. Moving on to our second point here, or this corresponds to this point, so now we're thinking about this point. This is going to be, is 4 in the subset? So we think about, is 4 in the subset, we have to think yes and no. Then we also have to think yes and no for the fact that 2 wouldn't be in a subset, so yes and no. Now since we want to include our last element of 6, 6 is going to be all of these terms, so we're going to think, is 6 in the subset? And we also have to think of each option in this case, so this is also yes, no, yes, no. Yes, no, these ones are a little cramped. Yes and no. All right, so we have all the options of thinking if each element is in the subset. So now we just follow the branches. So if we follow the very top branch, we're asking, is 2 in the subset? Yes. Is 4 in the subset? Yes. 6 in the subset? Yes. This gives us our subset of 2, 4, and 6. I'll use my mouse now and see if you guys can kind of see it a little bit. And where'd it go? Here it is. All right, so we can follow the mouse here. So we say, is 2 in the subset? Yes. Is 4 in the subset? Let's say yes. But let's say that 6 is not in the subset. This would give us our subset of 2 and 4, since 6 isn't in our subset. So we can do this again. So let's think about, is 2 in the subset? Yes. Is 4 in the subset? Well, let's go with no. We haven't really explored these branches, so we're going to say that 2 is a subset, but 4 is not in the subset. Is 6 in the subset? Okay, well, let's say yes, which in this case, our subset would be 2 and 6. Starting it again, we think is 2 in the subset? Yes, 2 is in the subset. Is 4 in the subset? No. Is 6 in the subset? Well, let's also say no. So in this case, our subset would just be 2. All right, so we've exhausted all of our branches where 2 is in the subset. So let's move on to not being in the subset. So we think is 2 in the subset? No. And let's follow the top branches of our no branch. So we would say, is 2 in the subset? No. But is 4 in the subset? Yes. And is 6 in the subset? Oh, let's also say yes. So this gives us our subset 4, 6. And let's try this again. So is 2 in the subset? No. Is 4 in the subset? Let's say yes. Is 6 in the subset? Well, let's say no. So in this case, this is going to just give us the subset of 4. All right, last 2. So we think is 2 in the subset? No. Is 4 in the subset? Let's go with no. But is 6 in the subset? Let's go with yes. All right. Now our very bottom branch here is going to be, is 2 in the subset? No. Is 4 in the subset? No. Is 6 in the subset? No. So this means that nothing's in our subset, and this gives us our empty set. So when we write these tree diagrams, our very top branch should always be the set itself. Very bottom branch should always be the empty set. These tree diagrams can be very useful, but I don't really suggest it for anything more than 3 elements. Because anything more than 3 elements, you're going to be just spreading off like crazy. But one thing we do want to notice here is that our tree diagrams give us this idea that our number of subsets a set of k distinct elements has 2 to the power of k subsets. So in our first case, we had 2 elements, 4 subsets. So this means 2 to the 2 power is going to be 4. Then for B, we had 3 elements, so K was 3 distinct elements. So that means that our set has 2 to the 3rd power subsets, or 2 to the 3rd power, which is 8, which is, we have 8 subsets. So now with this idea of our tree diagram, we can now decide how many subsets are contained in a set based on our number of elements. So if you had a set of 4 elements, then your number of subsets would be 2 to the 4th power, or 16. So example 4, we want to find the number of subsets for each set. We're not going to use a tree diagram for this. We're just going to be focusing on the property that we just learned. So we just want to find the number of subsets for each set. So we want to see how many unique elements. So for part A, we see we had 2, 4, 6, and 8. Well, that's going to be 4 unique elements. So k is equal to 4. According to our property, we want 2 to the k is our number of subsets. So in this case, our number is 4. So we have 2 to the 4th power, 16. So we know we have 16 subsets. Now for B, we're thinking about X, where X is a day of the week. Well, we know how many days in the week there are 7. So this means that K is going to be equal to 7. Now with our property, we know 2 to the power of K. This is going to be equal to 2 to the power of 7. And 2 to the power of 7 is going to be equal to 128. So this means it's going to be 128 subsets in the set of X being the day of the week. Technically, this will be the set of 1 through 7. Then, part C, find the number of subsets for the empty set. Now we can remember our property where a set is a subset of itself. So in this case, also, we want to think about how many unique elements there are. Well, an empty set has no elements. So k would be 0. So there's no elements. So then, since we know 2 to the k is equal to 2 to the 0 power, anything to 0 power is just 1. So we know there's only one subset. And we know there's only one subset because since it's the empty set, and we know that every set is a subset of itself, then itself can be its only subset. So one subset. Come on. Moving on, we see this image here in figure 2, and we have a box, and we have a circle inside of another circle. We see that the smaller circle is labeled A, the bigger circle, the blue circle, is labeled B, the A circle is kind of like a pink color. And then our rectangle here we see is labeled U. This is called a Venn diagram, if you've never seen one before. And we're going to use them to denote if an element is part of a set or not. So you see below, right above the words figure 2, we see A is a subset of B. And the way that we're looking at this is we're seeing that A is a circle that is inside the circle B. So we know that this is a subset since we see that the circle A is inside B. So moving on to our set operations, we can form new sets by combining or manipulating one or more sets. So given a set A and the universal set U, the set of all elements in U but not in A is called the complement of set A. So the complement of a set, looking at our book definition, we have let A be any set with U representing the universal set. Then the complement of A, colored pink in the figure, is A complement, which is also normally written as A with an apostrophe, or we call it A prime. Sometimes you'll also see it with A with a superscript or like an exponent of C. So you can see it written either way, but I think mostly we're going to be working with this A apostrophe. or A prime. So we say A prime is equal to X, where X is the property, where X is not in A, but X is in U. So if we're thinking about a complement or the complement of A or A prime, this is just going to be any element not contained in A, but is contained in the universal set. So thinking about example 5 here, we're defining our universal set as a set of 1 through 10, or 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. A is the set of 2, 3, 4, 8, and 9. And B is the set of 1, 2, 4, 6, and 7. And we want to find each set. So we're thinking about our sets within our universal sets when we think of our complement. So if A, we're thinking about A complement, or the complement of A, we want to think about all the elements that aren't contained in A, but all the elements that are contained in U. So we see our elements of A are going to be 2, 3, 4, 8, 9. All our elements of U are the numbers 1 through 10. So we see that A complement, or the complement of A, is going to be 1, 5, 6, 7, and 10. Because those are the values that are in U but not in A. Then moving on to B prime, or a complement of B. So B contains 1, 2, 4, 6, and 7. So once again, we want to think about all the elements that are not in B but are in U. So we have 1, 2, 4, 6, and 7. So this means that B prime is going to be 3, 5, 8, 9, and 10. Then for C, we have the complement of our empty set. Well, our empty set has no elements. And if we're thinking about all the elements in U that are not contained in an empty set, well, that would be all the elements of U. So we can say that our empty set prime, or just the complement of our empty set, is just going to be equal to U. I guess we could have written these as equals instead of arrows. Then we also, knowing this property, that the complement of the empty set will just be U, we have the complement of U is going to be our empty set, so this works both ways. This is because if we want to think about all the elements that are not in the universal set, that would be none of them, because they're all contained in the universal set, so that would be the empty set. Now we think about the complement of the complement of B. So this is basically saying we're going to take B complement, so all the elements that aren't in B but are in the universal set, and then we're going to take the complement of that. That's going to give us our original value of B. So if you take a complement of a set, that just gives you your original set. So the complement of B is just set B. All right, so moving on from complements, we have given two sets A and B, the set of all elements belonging to both sets A and B is called the intersection of the two sets. And this is written as A with what looks like an upside down U, B. So we call this A intersects B. So an example, if A is the set of 1, 2, 3, and 4, and B is the set of 3, 4, 5, and 6, then A intersect B is the set of 3 and 4. So you're looking for the elements that are in both sets, and that would be called the intersection. So in Venn diagram form, we see here that the intersection of sets A and B, shown in green in the figure, is A intersection of B, or intersects B, is equal to X, where X has the property that it is in A and it is in B. So the intersection, when we write our Venn diagram, that is going to be the section where the circles overlap. For example 6 here, we're going to let A equal the set of 2, 4, and 8, and B be the set of 3, 5, and 8. And we're going to let the universal set be all the numbers between 1 and 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we're going to find each set. So for A here, we have A intersects B, or the intersection of A and B. So let's just rewrite this, because let's visually look at our sets side by side. So our set of A is 2, 4, and 8. Write our intersection symbol. Our elements of B are 3, 5, and 8. So now let's look at terms that are in both. So 2 is in A, but 2 is not in B. 4 is in A, but 4 is not in B. 8 is in A, and 8 is also in B. So we see 8 and 8. So our intersection in this case is going to be 8. So that's our intersection. So that's the only number that they share. Then for part B here, we're doing A intersected with B prime. So let's write these sets out again. So we know that A is 2, 4, and 8. Then our B prime is all the numbers in our universal set, which is just 1 through 10, that aren't contained in B. So we know that B prime is going to be 1, 2, 4, 6, 7, 9, and 10. So now I want to look for the same values. So we see 2 is in both sets. 4 is also in both sets. But 8 is not, since this is B complement. So we see that 8 intersects B prime. That's going to give us a set of 2, 4. So we're just looking for all the elements that are in both sets, and those create a set itself. Two sets that have no elements in common are called disjoint sets. So in the Venn diagram here, we see that we have our universal set, our sets A and B, but they don't overlap at all. There's no intersection. So these are called disjoint sets. So an example, if A is equal to the set of 2, 4, and 6, and B is equal to the set of 1, 3, and 5, then there's no same element. And in this case, A intersect B would be the empty set. So disjoint sets, for any sets A and B, if A and B are disjoint, then we see that A intersects B is the empty set, because there's no elements that they share. Then we have that the set of all elements that belong to set A, set B, or both sets is called the union of A and B, written as A, which what looks like a U, B. So an example, if A were, so I guess just in an example, we have two sets, and we have the set of 1, 3, and 5, and we want to find the union between 1, 3, and 5, and 3, 7, and 9. That would become 1, 3, 5, 7, and 9. So it's basically you're combining the two sets, but you're not going to have duplicates of the same number. So you're just combining all of the elements to create one larger set. So in terms of Venn diagrams, we have the union of two sets, or the unions of sets A and B, shown in blue in the figure. So we have our universal set, our sets of A and B. We have A union B is equal to X that has the property where X is in A, or X is in B, or X is in both. So it's just all the elements contained in X and B, or sorry, A and B. So example 7, we're going to let A equal 1, 4, and 9, and B equal 1, 2, 4, and 5. C is going to be equal to 2, 4, 5, and 7, and our universal set is once again 1 through 10. So we see for part A, we have A union with B. So let's write our sets out so we can look at our sets next to each other. So our set of A is 1, 4, 9. We have our union symbol. Our set of B is 1, 2, 4, and 5. So this set is going to be equal to all the elements in A and B and both. So we see 1 is in both, but we don't want to write duplicates, so we're just going to write 1. 2 is in B, so it's included. 3 is not in either. 4 is in both. 5 is in B. 6 is not included in either. 7 is not included in either. 8 is not included in either. But 9 is included in A. And 10 is not included in either as well. So we see that A union B is going to be equal to the set of 1, 2, 4, 5, and 9. So it's all the elements in A, all the elements in B, and all the elements that they share. Now for part B, we have A union B intersection with C prime. So we have parentheses around A union B. So just like normal properties when we're multiplying things, taking exponents regularly in math, we always want to do whatever's in the parentheses first. So in this case, A union B is in parentheses, so we always do that first. And then we're going to take that result, we're going to take the intersection with that and C prime. Well, for part A, we already figured out what A union B is. It's going to be the set of 1, 2, 4, 5, and 9. So let's just write that. So we have 1, 2, 4, 5, and 9. And then we're taking the intersection with C prime. So let's find out what C prime is. So C itself is 2, 4, 5, and 7. So C prime, remember, is all the elements that are not in C but are in U. So C prime is going to be 1, 3, 6, 8, 9, and 10. And remember, we're taking our intersection of these two now. So by taking our intersection, we're finding the elements that are contained in both sets. Only both sets, since this is the intersection, not the union. So let's see. 1 is in both sets. 3 is not in the first set. 4 is not in the second. 5 is not in the second. 6 is not in the first. 7 is in neither. 8 is not in the first. You see that 9 is in both sets. And 10 is not in the first set. So this is going to be equal to 1, or the set of 1 and 9. So that is how you would do multiple operations at once. You follow the same kind of rules that you would normally follow in math. Then for our last example here, we can use all the things we've learned and we can put in practical applications to this. So let's do a more practical one. So we have a retail store classifies applicants by gender, marital status, and age. We're going to let U be the universal set, not to be confused with the symbol for a union. Let U be the universal set for all the applicants. Let F be female applicants. Let M be married applicants, and let Y be young applicants. Now we're going to describe each set in words. So we're just going to describe these sets. We're not actually going to be writing any sets. So if we just want to describe, let's do colon. We just want to describe this set. We have F and the intersection of M. So this is female applicants intersected with married applicants. So this is what we consider would be both. So in this case, we would say this set will include applicants that are female and married. Since we're considering only the ones that are contained in both sets. So we're thinking about female and married. So this set would also be known as the set of married females. So that's what this set would be. Then moving on to B, we have M prime union with Y. So if we have M prime, we know M is married applicants, so we're thinking about our universal set of just all of our applicants, but married, they're the complement of married, so basically not married, with the union of young applicants. So we would say this set will include applicants that are not married, young applicants and both young, let's go with unmarried applicants. So we know that this set of the complement of married with the union of Y, or young, we know that the set includes applicants that are not married. It also includes young applicants, and it also includes young unmarried applicants. So we have the separate sets, and then we have the combination. So it's 3 different things. Now for C, we have the complement of F intersected with the complement of Y. So we would say this set will include applicants that are not female in addition to also not young. This basically means that this is the set of non-female older applicants. So we see here when we take the intersection, that would be what we would consider both. So both characteristics, these applicants have to have both. But with our union, we see it can be one or the other or both. So we can really use a lot of these things that we've learned about sets. We can use it in applications in real life. We can use it in terms of math. And there is many different ways that we can manipulate these sets and rewrite them in many different ways. So that was definitely more of a content-heavy chapter. If you have any questions at all, please do not hesitate to email me, pop into my office hours, put in a question into the anonymous question form, or anything along those lines. So I will see you all virtually later.